Yeah, welcome everybody. I assume you already know that you can learn from your data much more effectively and efficiently than using trial and error or one factor at a time experiments. The better approach is a statistically designed experiment, or DOE, which is one application area in JMP. As you can see from our customer stories, so this is the application area in the browser. You can get at the JMP in action menu, and on the same menu you find the customer stories, which show you that JMP is also a leader in industrial experimentation. And many companies use JMP to better understand their systems or processes and to make better predictions into the future. However, the most important part in our session title today is teaching. And I will neither introduce you to the theory behind DOE, nor will this be a JMP how-to seminar. Instead, I want to inspire you by several demos, which you can either watch from a lecturer's or from a student's point of view. You will see live demos using classical and custom designs, and also of modern and specialized designs. And before wrapping up today, I'm going to recap some tips and resources for teaching. As always, you can easily follow all links by downloading this journal from our academic webpage, the landing page you find at the same menu on jump.com, and there go to the academic webinar library or directly go to jump.com/teach. While you are not posting any questions into our Q&A chat, it's now time to lay back and to enjoy the demos. As a student or a researcher who just installed JMP Pro 13, where to get started designing a first experiment. So browsing the JMP menu for the first time, the JMP starter sounds like a good starting point. By clicking on DOE, you get a structured overview about all relevant platforms. You see the custom designer and augment design, definitive screening, design and analysis, more classical or traditional designs like screening designs, response surfaces and mixtures, diagnostic platforms to evaluate or compare designs, and consumer studies including discrete choice experiments and MaxDiff, and also some special purpose designs including space filling designs for computer experiments or nonlinear designs. Hitting the help menu in JMP, let's have a look at the DOE tutorial you can also send your students to. And there's a good reason why this gets you to the custom designer in the first place. Yeah, you can also read about this in the introduction coming with that tutorial, but you see that the custom designer is an all-purpose tool which is useful in most situations. And an optimal design is created by your computer. You could end up with a classical textbook design, but you don't need to worry about the bells and whistles of different design types. And if a better design exists, your computer will automatically find it based on an optimality criterion which can be chosen by JMP according to best practices or by yourself. So let's get started. So I move on to the next step, which is about defining a response. And this should be yield, and the goal is to maximize the response, and the low value is 0 and the high value is 20. So that's the response, and we can move on to defining the factors. And the tutorial tells you that there are two continuous factors. The first one is called die position, and this goes from 120 to 140. There's a second continuous factor called catalyst, which has a low value of 10 and a high value of 20. So now our two factors for this experiment are set, and we can click on continue, which leads us to the model definition. So here we specify what we want to learn about, and this is just to learn about the main effects. So we have the intercept and the two main effects as model terms added. So I move on to the next topic, which is about the budget. How much can we afford? And here JMP suggested 8 runs, but I want to spend 12 runs. Let me just check the model. Because the model, let me go back, so you can always go back a step right to the beginning defining responses. But here what I didn't change was extending the model to learn more than just about the main effects. Yeah, so this tutorial also suggested let's just add also more complex terms to our model, which include both quadratic terms and the two-factor interaction. Yeah, so this is already a response surface model you can get by clicking on RSM. And for this model complexity, JMP suggests 12 runs, but we can only afford 10. So I change the number of runs from 12 to 10. So the budget is set. So now I can click on Make Design, and JMP creates a design for this problem. So we have no constraints defined, but that would be another option as well, to have zones in your design space you don't want to use. So here we can look at the design. So we see our 10 runs and the values to use, the low, high, and center values for our two factors. And before creating the table, we can check the design and the quality of this design. So this is a response surface. So maybe we are interested in optimization, and we want to predict the response as accurately as possible. So we can look at the prediction variances in different ways. So this is the prediction variance profile. So we see traces for all factors and the relative variance over the design space. And if you wonder what this is about and how this is calculated, you can use the help tool, drop it here, and you get context sensitive help explaining what you see in this output and also how the relative prediction variance is computed. You can also look at the surface to see a 3D surface of the prediction variance for the two factors and the variance on the third dimension. So here we see that this is an eye-optimal design, which minimizes the average prediction variance over the whole design space. So I move on to the next topic, and now we can make the table. And let me show you the first table. So this is the basic design table you can just use and run the experiment and add the yield measurements to the response column. Yeah, another interesting option is if you want to get some values to play with and to explore further, you can also tell JMP to simulate response values with the design. So if I make another table now, you see that we can simulate response values, and the yield column is already filled with some randomly simulated values. And there is also a simulation column, another column, which has a formula. So here I can change the model effects. So the interaction, I choose 3, so I make this really strong compared to the other effects. And the catalyst quadratic term, I make it also stronger, so medium strong compared to the others, and also compared to the error standard deviation. And now I can click on apply, and you see that the formula takes the values set here for the effects plus the random error and simulates new values every time. So now from here I can run the model script. By clicking on the green triangle, and this shows us the response surface model. The output is optimized for screening, and instead of yield I can also use the latest simulated yield column for this report. I run the model and I look at the effect summary, and here we see that the interaction is most significant and the main effect of dye position is least significant in this example. There's some diagnostic output, and we can also look at the parameter estimates and the p-values showing us the significance for the different parameters as well. But the best to understand the model and how the model works is the profiler, in this case the prediction profiler in JMP. So here I can change one factor at a time, and we see how this influences the response. So this is the simulated yield in this case, but we also see the interaction if we look at the trace of the other factor. I can also add desirability functions which show you what the initial goal was. So we wanted to maximize the yield, so JMP remembers that, and here we see the desirability, the higher the better. So that means that I can ask JMP to optimize the factor settings according to what we want, according to desirability. And we see that these settings, the red settings, give us the highest yield of 10. Okay, let me close this introductory example, which was already more than just a hello world, but you see that the custom designer is really a step-by-step assistant and guides you through all the steps to define your problem. And all the decisions you make during these steps will be stored and JMP will remember later on, especially when it comes to the analysis of your experimental data. So as you see, a JMP design table is really a central element. It is the output from your design, and after adding the response data or simulating response data, you're all set to launch your analysis. And let us look at a design file again by opening this sample data set bouncedata.jmp. So here we see for this data set that this is a Box-Behnken design. So this is a response surface design. And from this design table, I can go back and see how this table was created. So I can go back to the DOE dialog and right back to the response definition. And here we see that the response is stretch. And the goal was set to maximize a target of 450. We have no model set here because this is the response surface design platform. So the model is already set by the platform selected. But as always, you see many tools to evaluate the design at hand. So one of them is the color map of correlations. So here we see that the main effects are not correlated, and they are also not correlated with second order effects and even third order effects. So we will come back to that output later because this is really a central element in evaluating and especially comparing designs. Looking at our data table again, we see that the response has the response goal saved as a column property, a response limit, and this tells JMP so this response should match a target. And also the factors are coded as design factors. This design can be analyzed by clicking on Model to go forward, or I can also choose an analysis platform like this here, fit to level screening design, to analyze the data. So I choose my factors and the response, and JMP uses the screening platform and some Monte Carlo simulation to identify the best factors, and I run the model from here. So the most important model effects are already selected by the screening platform, and I'm ready to build the model. And we see that the most important effect is the two-factor interaction between silica and sulfur, and we get diagnostic information and again the profiler, which shows us the traces for our factors. Okay, so that was a sample data set. You can also get from the help menu sample data. Let's move on to classical designs. When you want to teach the foundation of DOE, so start very basic, like one continuous response and one categorical factor leading to a one-way ANOVA. You won't start on a green field, of course. So one option is to use a self-paced, web-based training from SAS Education. I show you that online. So we have several e-learning courses for JMP software, and there are several courses for DOE, and the classic design of experiment course. So this is what you can learn here, and this is a course about 16 hours, but don't worry about the fee because these e-learning courses are included in an academic site license already. So let me show you the course notes. So from these courses you can also get the content and then just use some demos, examples, exercises in your own class. So for instance, here in the course notes we see that there is an experiment, a very simple one factor. So this is about the hardness of drill tips, and there are 4 different sorts of drills. And according tips in 4 colors, and hardness is the response. And you also get a JMP journal, and you can use that one to look how the course is going through all the lessons. And here you see this example is also used during the basic chapter to introduce DOE, and here you get the data set. Again, this is a JMP design table, so you can go back and look at the DOE dialog. As I said, this is a very simple, one response and just one categorical factor. And this is a factorial design, of course, and we can look at Graph Builder to explore the data. So I can put hardness on the y-axis and then tip type on the x-axis. Oops, so let me start over. Oops, sorry. This seems to be maybe that's the problem here. There's nothing in, because that's the additional empty table with an empty response I got from the DOE dialog. So let's go back to the full table with hardness filled out. So this is the one you get from the journal. Now, based on that one, I use Graph Builder, and now I take the filled response column on the y-axis and I look at tip type, and maybe you want to look at box plots and at the data points again to get some idea if the different types of drill tips make a difference regarding hardness. Maybe the more sophisticated approach is of course fit y, which is hardness, by x, which is tip type, and then you get to a one-way ANOVA analysis where you can also add box plots or means ANOVA output, and we see there is some difference, and you can ask for comparing the means to see where the difference is, and you see there's a significant difference regarding the mean, the group means, between the blue drill and the other ones. So this was an ANOVA output, and you can also save the residuals, and then from there you can check assumptions, of course, and normality. And if you're more interested in teaching ANOVA and regression, I would like to recommend another recorded webinar of my colleague Ruth Hummel, which you find in the webinar library as well. More course material, also from other lecturers, is shared in our course material library, and this can be found at jump.com/teach, and there go to course material library and then design of experiments. So here you also see some other material, including this here, which is lecture material from Phil Ramsey, professor at University of New Hampshire. And one introductory chapter Phil is using is about interaction effects in factorial experiments, with a case about breeding shrimps. And you get also access to all the data sets and also all the lecture videos online. So this is the data set for this example. And the response of interest is the weight gain, and we have three continuous factors: temperature, density, and salinity. So let me start with a distribution. I just run the script here, and we see that we have 12 treatments and 3 replicates per treatment, so an overall of 36 runs. And we see that this is a balanced design. And there is also a center point for salinity, because in this case some curvature was expected for this factor. This can also be confirmed by using Graph Builder. So I add weight gain to the y and salinity to the x-axis, and you see, oh, indeed, so there's some indication for curvature for this factor. I can also look at temperature instead. So weight gain by temperature, but now I use salinity to overlay the graph. And here we see that there's an interaction. Yeah? So the relationship between weight gain and temperature depends on another variable, which is salinity. So this is maybe good to know, and also for modeling later on, so that there are some curvature and interaction effects which seem to be active in this scenario. So for analysis, I just run this script here, and we get also already a reduced model, and we see the significant effects for this model. And as always, I can go down to the prediction profiler, and we see the curvature for salinity, which is really clear. And changing salinity, you also see the interaction if you look at temperature, and also the other way around, of course. And we have 2 linear effects for temperature and density. So if you want to use this model for prediction on new data, you can take the top red triangle, and from there save columns, save the prediction formula. And by doing that, you get another column in your data table. So we already had this one here, and this is a prediction formula. So you see there's a plus sign, which tells us that this column has a formula, no static values. You can click on the plus to open the formula editor and see the equation. Or you can use the formula column, for instance, on a surface plot. So here I look at this prediction formula, our model, and here we see the model, the plane for temperature and density, these 2 variables. And if we look at salinity instead, you can also see the curvature effect of that factor. So this and many other examples can be found online, and you get the link on the journal. So let's move on to custom designs. And while the classical designs are helpful in teaching basic concepts, so they are not really flexible enough in most real-world situations. So therefore, experimenters in industry prefer the custom designer in JMP to get the optimal design for a specific problem. So let me show you some options during the step-by-step creation of a custom design for tasting wine. So this is an example taken from our DOE guide on help, books, and then design of experiments guide. And the factor table I just opened by clicking here can be also found in the sample data plus the wine data as well. So in this scenario we will have 5 wine experts or raters, each of them testing 8 wines. So 5 times 8, 40 runs. The question is which type of wine our raters really like most from 0 to 20. So I start DOE custom design and the response is the rating, and we want to maximize it, the higher the better, and the rating goes from 0 to 20. So this is the response definition. Yeah, so the factor table is already open, but as I said, so this is a special design. We have 5 raters. It's a special situation because we assume that responses of one rater are more similar than responses between raters. And this variation can be purged by adding a blocking factor to our design with 5 levels for 5 raters and 8 runs per rater or per block. So I choose a fixed blocking factor and name this rater. And then I also load all other factors from the factor table. And now you see that all factors are set. So the blocking factor rater plus 9 other factors, which are all categorical and easy to change. Yeah. Every rater can test 8 wines, so we can have a total of 40 runs. And now you see that this makes 5 raters testing all these combinations of wines. And the assumed model that we want to learn about is just including main effects, as we see here. Main effects only, and all parameter estimates are necessary. We have no constraints. And here we see alias terms. Alias terms are not in our model, but they will be analyzed for aliasing or correlation with the terms which are in our model. So in other words, we can see if an effect in the model can be biased by an active effect which is not in the model. And that's definitely something to worry about and to think about. Yeah, so here we see that the documentation suggests to use this random seed, and this can be entered here, set random seed, so that we get the same random design as in the documentation. This is maybe useful as well if you do this in a class and you want that every student ends up with the same, exactly the same design, and not just gets random versions of the same level of designs. So now we are ready to go make designs. So here we see the design for all the raters. We can look at the design evaluation, and here we see the color map for correlation. And we see that there's no aliasing or correlation between main effects, but there's some aliasing going on between main effects and two-factor interactions, and also between second-order effects. Okay, I click on Make Table, and this is the design table with an empty column for rating. Also here we can check that our main effects can be tested independently, so we see that every rater gets all the settings, different types of wine, and you can see that the design is well balanced and that the factors can be tested independently. So I close this design table because we have the version which includes the ratings from our testers, and here I can click on Model to analyze the data, and you see a main effects model, and I click Run to build the model, and I go directly down to the prediction profiler. And now the question is, what is the best type of wine? Maybe somebody says, stop, sorry, we cannot change to Dijon, we have to use Bernard. And if that's the case, you can also lock a factor before you optimize, before you look for the highest ratings by doing an automatic optimization. And here you see that even for Bernard, which is suboptimal, we get an average rating of 18.4. So that's the optimum, and if you're interested in the variance between raters, so you can also choose to reset the factor grid and show the raters on the profiler as well. So now we see the raters here, and we see that the rater number 1 has on average the lowest ratings, while rater 3 has the highest. And you can also see the influence what you could get if you would be able to change it to Dijon variety of wines. So you can read more about this example and of course many other examples in the documentation. The next example here is from a great book about optimal design of experiments from Brad Jones and Peter Goose. And one of the case studies discussing real-world problems and solutions is the wind tunnel experiment. And that has hard to change factors, which are best implemented using a split plot design. Another flexibility you get by the custom design tool. So here's the JMP data table, and let me show you the design as well. So I click on DOE dialog, and this one uses 130 starts, so that's another option typically used in industry, so to do many searches to really get the best design you can. And this is the best one here, and the special thing is that we have whole plots. So we have 50 runs in total and 10 whole plots in this case, and the two factors which are hard to change are the height factors for the front and rear right. And you can see this if you go back to the responses. You see we have 4 responses, 3 to minimize, 1 to maximize. But the special thing here is these 2 factors have been set to hard to change factors. The changeability is hard to change. So why are they hard to change? Yeah, because there's a lot of effort to change them randomly from run to run, because every time the wind tunnel has to be shut down. So they decided to combine the same settings into whole plots. So that's the reason to have 10 whole plots, keeping the settings for front right and rear right height constant. So I can evaluate this design by clicking on the script, evaluate design, and for instance we can look at the estimation efficiency. And the estimation efficiency compares the confidence interval length of this design, the current design, with an ideal design. So this metric here is 0 for an orthogonal d-optimal design, and it increases when your design becomes less ideal. So we definitely have a price to pay for changing some factors not at random. And the analysis in this case is also a bit more sophisticated, because this design is not completely randomized and the runs are not independent anymore. But JMP knows how to handle it. So the stored model script uses RAML as the analysis method, so restricted maximum likelihood, to estimate the model parameters. And when I run the script, you see the results. So here we see the effect summary and parameters for the first response, which is drag. And looking at the parameter estimates, you see that the standard error for the 2 hard to change factors is maybe 3 times higher than for the easy to change factors. And also the degree of freedom is much lower, so there is much less information for whole plot factors, and there's not that much information to learn from, because the factors are not changed that often. So if you're interested to watch the full story behind this case study, a recording by Peter is available online, and you find the link in the JMP journal. So JMP also supports many topics for more advanced courses about DOE. For instance, mixture designs, consumer studies, or computer experiments. Let me just give you an idea and show you a few examples. So the first is a must-see, because this is a modern design. It's called definitive screening design, and this one has been developed by Brad Jones and Chris Nachtsheim just a few years ago, and it belongs to the most famous modern approaches in experimental design and screening designs. So our info kit about teaching design of experiments in chemistry, show you the webpage, explains the benefits of a DSD in detail by solving the same problem in 2 different ways. First is a 12-run custom design for screening plus a 6 augmented runs design for optimization using an RSM. So a total of 18 runs. And secondly, a single 13-run DSD, which gives you the same information while saving almost a third of the total runs. So here are some highlights. This is a data set. We have 5 continuous factors, and yield is our response, and the response data is filled in. So we can look at the distributions. So here you see this is a 3-level design, and that allows to test curvature for every factor. Not just curvature globally, but you can check where a curvature occurs. Also run the DOE dialog and then look at the color map on correlations, and this is really the beauty of that design type. So you see that there is no correlation between main effects and also no correlation between main effects and second order effects, and also the correlation between 2-factor interactions is pretty low. And if the number of effects is low, so that's the effect sparsity, which is often the case, screening and optimization can collapse into a single step. And then there is a special platform in JMP for analysis. It's called Fit Definitive Screening Design, which does everything for you. So here you see the main effects plots, and you also get a profiler, and you see curvature effect for time, and you can run the maximization and see the best settings. That's a definitive screening design in a few minutes, but it's really worthwhile looking at that topic because you can save a lot of money and time and get to better results. 2 other examples. So the first is from consumer studies. So a typical question in marketing is how to design a product or a service your customers really like. So there's also a sample data set about laptops. These are not the most recent ones, but that doesn't matter. So we see attributes for these products, which are disk size, speed, battery life, and price. And they were presented to respondents, to test persons in choice sets of 2. Yeah, and then everybody had to choose the preferred one over the other. And this information is given here. And if we look again at distribution, so we see this here, and you see that the respondents took part in different surveys. So there were 2 surveys, and you can also see the influence of speed. So this was highly preferred over lower speed, and of course disk size, higher disk size was preferred over smaller disk size, and the higher price was of course not preferred. So this can be seen here in general, but you want to compare these attributes and how much value is behind maybe doubling the disk size. Yeah, and for that there's also an analysis platform in JMP for choice experiments. And this one, I just run the model for this one, gives you a lot of information here. So we see that speed seems to be most relevant for consumers choosing laptops. But you also get a profiler, in this case a utility profiler. Yeah, and by looking at the price, you see that $500 difference correspond to a utility difference around 2. Yeah, and doubling the disk size from 40 to 80 gigabytes corresponds to more or less a utility of 1. So this improvement here has maybe a monetary value for the consumers of $250. Yeah, so half of this difference. So these are conclusions marketing can make easily from such discrete choice experiments. And the last example is a special one. So this is about a physical experiment. And in physical experiments, your process response this is about a computer experiment. And in physical experiments, the typical experiments, your response is random. Also because of measurement errors and many influences. So you model the signal and you want to eliminate the noise. A response in a computer experiment is simulated by a simplified model of the real world. And for instance, simulating climate changes. And this output is computed and deterministic. So it's a different scenario, and you don't need to worry about randomization or replication anymore. So in these scenarios, so there are special design tools and approaches and also special analysis tools which are typically used and which are available in JMP. So one example is on the DOE menu, and then special purpose space filling design. So I use one response and I add a third continuous factor. I continue, and then I choose this one here, let in hypercube. Maybe 90% of all computer experiments in industry use still this design type. And you can see the design diagnostics as well, including minimum distance between design points and so on. And I choose to simulate again, and I make a table. And here we have the table, and I assign coefficients, anticipated coefficients to our effects of 1 and 2 and 3, and I keep the 1. So that's can be set to 0 because it's a computer experiment, and by clicking on apply, so we see that the response, the simulated response, is the same. Why simulated? Because there's no random error anymore. And this can be shown in a scatter plot right now. So I can choose graph and scatter plot 3D, and then I take the 3 columns in here, and I can color by Y simulated, and then I click OK, and here maybe I change the marker size, make it a bit bigger, and also the coloring just by right click and then change the settings. So maybe this is better to see. So now you see the 3-dimensional design space, and you see the simulated response by color from green to red. And for analyzing these type of experiments, so again it's the same approach, and you use, let me go back to that one, special purpose space filling. So I had another one here, and I simulated responses. Make table. So I have to close this one, and here you see, so all these design tables have a modeling tool attached, as all JMP design tables, and this one uses a Gaussian process model to analyze computer experiments. Yeah, and you see here the marginal model plots for the three effects, but I can also add a profiler again, and then you see the influence of our three factors. Okay, so we only have a few minutes left. This is just a recap about tips and resources so we recommend to use. So I would suggest you have a look at these sections in the journal later, so you have some options on the red triangle we saw, especially simulating responses, which can be done manually but also automatically, which helps to use formula columns in automated randomization tests. So that's another cool feature we didn't see today. It's a best practice not to just have a one-step experiment, but multiple steps. And then on the second step, you learn more and you add more information to what you already know from the first step. So this can be done by choosing Augment Design from the DOE menu. And then use all the diagnostics. And there's one tool set which is available under Design Diagnostics, Sample Size and Power. So these are calculators to calculate sample size and power. So if we have this standard deviation and we want to detect this difference, so then I can see the sample sizes and power relationship by clicking Continue. Yeah, and then you can read this very easily. So for this scenario, how does the power relate on sample size? Plus compare designs, and that's the last thing I want to show. Comparing designs is really useful. So to compare all the evaluation outputs. So I open two sample data sets. So this is a 20 run design, and I want to compare this to a full fractional design, which is a 32 run design. So let me choose compare these two designs. So that's the full factorial, and I add the 20 run optimal design created by JMP, and I click OK, and now I can compare them side by side. So here we see the power analysis, and the power is 1 for the full factorial design, and you see there's some price to pay. There's a lower power for the 20 run design. And you get more information about power. You get a lot of information about prediction variance, and this one here shows you the fraction of the design space, and you see that the median prediction variance is much lower, maybe half for the 32 run design compared to the purple or the blue, which is the 32 run design. So 20 run design, it's doubled, of course. So you have a higher variance if you only spend 20 runs. Yeah, a lot of other information, including confounding. So we see that both designs have no factors completely correlated or confounded. And you also see the correlation maps side by side. So that's a nice comparison as well. And for resources, just browse the webpage I showed you earlier. And there's one book I want to recommend. That's a pretty new one. And this discusses 80% of the book, the need for smart experimentation and designed experiments. And that's the book Problem Solving for New Engineers by Milisa Bouye. And this is really a great book to check out. And this is about the why and the how of designed experiments. So there are two other books which are available. So an addendum for the classical Montgomery DOE book, plus the famous one about optimal designs, of experiments, a book with a lot of great case studies, including split plot designs and blocking and covariates and very nice, interesting scenarios you can read about.